Hi there. In this video, we'll take a look at virtual address formats in the 64-bit ARM architecture. So a virtual address is split into its upper bits and its lower bits, where the upper bits are used to identify a physical block of memory, and then the lower bits denote an offset within that block. Identifying the physical block of memory involves passing the upper bits through the memory management unit, or MMU, to perform address translation by walking the translation tables in memory. So the MMU uses the upper bits to index into the translation tables, where each entry in the table holds the base physical address of a block of memory and the attributes corresponding to that block, such as the memory type and the access permissions. In practice, there will be multiple levels of translation table, where entries can either point to a physical block or to a next level table. To facilitate this, the upper bits of the virtual address are further split into separate fields. Here, the first level field from the virtual address is used to index into the first level table, where each entry can either point to the base address of a physical block of memory or to a next level table. And in that case, we take the next level bits from the virtual address and use those to index into that table. And the entry here will finally give us the base physical address of a block of memory, which we can combine with the lower bits from the virtual address like before. The idea here is that earlier levels map coarse grain blocks, whereas later levels map finer grain blocks. Using these next level tables does come at a cost though. Firstly, we need more tables, which each consume additional memory, and there's also additional lookup overhead if we miss in the TLB. Okay, so the ARM architecture supports 3 different translation granules, which represent the smallest block of memory that we can map, and those are 4K, 16K, and 64K. 4K is the one that's used most often, and is also the only one that's available on older versions of the architecture, so that's the one that we're going to go through first. So to address each individual byte in a 4K block requires 12 bits, so that's the bottom 12 bits of our virtual address. We're going to have more than 4K of memory in our system, and at that point we need a table to index between those different blocks. And we call this the level 3 or L3 table. This L3 table occupies exactly 1 granule of memory, which is 4K, and each entry in the table is 8 bytes because they are 64-bit descriptors. We therefore have 512 entries in our L3 table, and to index each entry in that table therefore requires 9 bits of our virtual address. 512 entries, each mapping 4K, means that our complete L3 table maps 2 megabytes of memory. We're going to have more than 2 megabytes of memory in our system. At that point, we need another L3 table, and that also means we need an L2 table to index between them. And we just discussed that a single L3 table effectively maps 2 megabytes. So actually, our L2 table can also point directly to 2 megabyte blocks instead of pointing to L3 tables. As with L3, each L2 table is 512 entries and so requires 9 bits of our virtual address. 512 entries, each mapping 2 megabytes, means that each of our L2 tables effectively maps 1 gigabyte of memory. Now, we may have more than 1 gigabyte of memory in our system, which again would require another L2 table and therefore an L1 table to index between them. We know each complete L2 table effectively maps 1 gig, therefore L1 tables can directly point to 1 gigabyte blocks. As with L2 and L3, each L1 table is 512 entries, so requires 9 bits of our virtual address. 512 entries per table, each mapping 1 gig, means we've got 512 gigs mapped per L1 table. We may have more than 512 gigs in our system, which would require another L1 table and an L0 table to index between them. However, there is no option for an L0 table to point directly to a block. Now, as with all of the other levels, each L0 table is 512 entries, so it requires 9 bits of our virtual address. And that means that our full 48-bit virtual address format looks like this when we're using a 4K granule. So we've got a 9-bit L0 field, a 9-bit L1 field, a 9-bit L2 field, a 9-bit L3 field, and finally a 12-bit offset field that denotes the offset within each physical block. Now, if translation ends early, unconsumed bits are added onto the block offset. So for example, let's say we have an L1 entry pointing to a 1 GB block. That means we have 9 plus 9 plus 12 unconsumed bits from the virtual address. So these all become our block offset. And you'll notice that 2 to the power of 12 plus 9 is exactly 1 GB. Now, when using a 16K granule, we need 2 more bits to address each byte in a 16K block, compared to when we had a 4K block. Also, the rule that a translation table occupies 1 granule of memory still applies, but our granule is now 16K. This means that there are 2048 entries per table instead of 512. So again, we need 2 more bits of our virtual address just to index into our tables. Now we can step through the example like before, and we'll see that once we've got more than 32 meg, we would need more than 1 L3 table. Therefore, we'd need an L2 table to index between them, and this means that our L2 entries can point directly to 32 megabyte blocks. And again, stepping back through this, we get 11 more bits consumed at L2, 11 more bits consumed at L1, but that means we only have 1 bit left at L0. This means that our L0 table is a very small table with just 2 entries. So this represents the full 48-bit virtual address format when using a 16K granule. So we have the 14-bit block offset, 11-bit fields for L3, L2, and L1, and finally a 1-bit field for L0. You can therefore imagine that at a 64K granularity, we'll have even less bits remaining. In fact, we only have 6 bits remaining when we get to L1, and we have no bits at all for L0, so we don't have an L0 table at 64K granularity. And in this example here, our L2 entries would therefore point to 512 megabyte blocks, because we'll have 8,192 entries per table, and each entry maps 64K. Thanks, hope you found that useful.